All right, today we are in section 10.4, and section 10.4, the main topic is work. Okay, so what is work? Let's define that first before we get into the rest of this section. All right, so work, simple enough, is the transfer of energy from one object to another object. All right, whether that's pushing something, lifting something, pulling something, however you may push, pull on another object, but is the transfer of energy from one object to another. Okay, and what we kind of say that is this object does work on another object. Okay, now let's say you do push an object. Okay, you push it across the ground, it moves, and then when you're done pushing, it's not moving anymore. Okay, did that work just disappear? Okay, well, hopefully at this point you know that nothing can be created or destroyed. No energy, no matter, no nothing is destroyed or disappears. Okay, and so when you push something, even if you push really hard, it doesn't move at all. All right, you still gave work to that object. Now, where did it go? It may have gone to heat. It may have gone to sound. It may have gone to many other different forms of energy. Okay, not all energy is kinetic. Not all energy is in movement. Right, so it could have caused some high friction and warmed up the object. It could have collided and impacted the object and dented it, or created some sort of potential energy in the object, whether that be for falling or for a temperature heat kind of thing. All right, so now that we have kind of defined work, let's talk about how we talk about that in science. Right, so the unit for work is power. All right, the way we describe how much work something is doing is power. All right, now what is power? Power is work over time. All right, so power is work over time. All right, and the unit for this, right, is what we call a watt. All right, so you've probably heard of energy, or like in your electricity, they talk about how many watts something is. That is the amount of work or energy that it takes over amount of time. Okay, and a watt, 1 watt, okay, is equal to 1 joule of energy over 1 second. Okay, so 1 watt is 1 joule per second. But that is how we discuss in the units for work and power. All right. Now, being complicated, Americans and a few other countries don't quite use the metric system, all the same measurements. So we have our own unit for power, okay, and you've probably heard it before. It's horsepower, okay. Horsepower, funny enough, is actually, well, originally was actually defined as the ability of a horse to lift 550 pounds 1 foot in 1 second. Yeah, that means a lot to you, I'm sure. But on simpler terms now, 1 horsepower is about 745.7 watts. So that is what a horsepower is equal to. If you ever have to calculate that, not that you might ever have to, but if you're a big car person, who knows? Maybe you want to know the watts of power on a car. Or if you get into some sort of industrial work and later on in your life, there could be conversions that you need to know when you're converting energy into horsepower, especially when it gets to like electric motors, things like that, because you can kind of directly define the amount of energy a battery has to the amount of power it can put out. So the next topic we're going to dive into is momentum. All right, and momentum is kind of briefly described as the movement of an object, or the weight behind an object's movement. People talk about momentum. They talk about a movement of, a society is moving. They have momentum. Our campaign has momentum. All right, but in science, we're talking about the actual object and its power, its potential to do work. Okay, so momentum, all right, symbolized by lowercase p. All right, that's momentum. All right, and it is equal to the mass of an object, the weight of the object, times its velocity. So how fast the object is moving. All right, so the heavier an object is, the more momentum it's going to have. And the higher the velocity, the faster the object's moving, the more momentum it's going to have. All right. Now, let's say you have a bowling ball rolling at 5 miles an hour and a pillow flying through the air at 5 miles an hour. Well, the bowling ball is going to weigh more. It's going to have a higher momentum. Okay. Same thing if you took 2 pillows and one pillow was going 5 miles an hour, the other pillow was going 500 miles an hour. Well, the one with 500 is going to be it's going to have a lot more momentum. It's going to be pretty dangerous. It's not a pillow you want to get hit by. It's moving that quick. All right, so the higher the velocity, the higher the mass, the more momentum you have. All right. Now let's talk about collisions. Okay. Obviously, when one object is moving, if you let it move long enough, well, there's a wall right there. Eventually, you're going to hit something. Okay. Now, just like everything else in science, nothing is created or destroyed. All right, we have to remain constant. So our total momentum, the total momentum in the area or the objects, has to remain equal. Okay, and we'll get into this a little bit more. There are static collisions and there are elastic collisions. There's different ways objects translate energy to each other when they hit. But on a simple basis, the total momentum, so momentum, little close p, total, is equal to the momentum of each object. So we can say object 1 plus the momentum of object 1 and object 2. Alright, so total momentum is equal to the sum of all the momentums in the system. Alright, so if one marble is moving and the other is not, alright, you add those together, then the marbles hit, add the two numbers together again, and they'll still be the same. Okay, this marble might have taken a little bit from this marble. Depending on how heavy one object is to the other, you may not see the same speed, but you're going to see the same total momentum. Okay, so let's look at that real quick. Let's say that you have a marble that weighs, we'll go with our 10 kilograms. Okay, 10 kilogram marble, and it is moving at 5 meters per second. Okay, that's our first marble. This is this guy right here. Alright, his momentum is 10 times 5, or 50, right? Our overall, I'll get 50 here. Alright, now he hits another marble, right? And that marble is not moving. Okay, let's say he weighs 20 kilograms. Well, we'll say 5. It's a smaller marble, obviously. 5 kilogram marble that is moving at 0 meters per second. It's not moving at all, right? Alright, so 5 times 0, that's 0. So this object has no momentum. Okay, so add those together. 50 plus 0, our total momentum is 50. Okay, now, I'll erase my marble. These marbles run into each other. Okay, and the resulting speed of our first marble, the weight doesn't change, all right, is now 2 meters per second. All right, it hits this marble and this one slows down, right? It loses some of its momentum. Okay, so 10 times 2, the new momentum here is 20. All right, now if our momentum was 50, okay, and now all we have is 20, there's 30 momentum stuck somewhere, right? So we can say the momentum of this is now 30. All right, so pull up our equation. P equals m times v. We don't know how fast this marble is going, but we know it weighs 5, and we know the momentum is 30. So 30 divided by 5, this object is going at 6 meters per second. Now, everybody see that? I plugged in 30 and 5 into this equation, solved for the v, and we got 6. All right. Note that this object is now going faster than the first object was. All right, but it's because a lighter object was hit by a heavier object, right? We can gain speed, right, by sacrificing some of the weight that was behind it, right? Partial momentum, only 30 of the momentum, all right, can speed up a smaller object much faster than it can speed up a heavier object. All right, I think that's... All right, the last concept for this section is momentum versus kinetic energy. All right, and now, you're probably sitting there thinking these things sound very similar. When you try to think of it, if you try to explain the difference, you know, we're talking about objects in motion for both of these, right? But the difference comes in the ability to transfer, okay, or how things are transferred between kinetic energy and momentum, okay? So imagine that you have a baseball bat that weighs, I don't know how much baseball bats weigh, 5 pounds, okay? And you have a wooden stick that weighs 5 pounds. All right, if you swung them at the same speed, they would both have the exact same momentum. All right, now, you hit a baseball with those. Which one's going to go further? A stick hitting a ball or a nice bat that has been designed to hit the ball? All right, well, more than likely, all right, assuming you have a good hit or however that may be, the baseball bat is going to send the ball a lot further. All right, but with our momentum equation, P equals mv, okay, there's no difference in the bat and the bat and the stick. All right, but what kinetic energy allows you to calculate that difference of being able to translate the energy. Okay, when we talk about momentum, we have collisions, and collisions are almost never full. All right, they almost never completely deliver the energy right behind them. Right, they bounce off, they deflect. You know, when two cars hit each other, as terrible as that is, you know, they hit and it just does damage and translates energy. But one car goes off this way, one car goes off this way, right? When you're talking about a baseball hitting a ball, the bat is going to deliver a lot more of that energy where it needs to deliver it, right? It's less energy delivered in your hands, more energy delivered at the ball, and it also deals with amount of time that there's contact, right? When two different materials hit something, right? Let's say that you hit me, well, you're going to squish in a little bit. I'm a bigger guy, all right? And then you're going to get pushed back. All right, but if you hit this wall, you're going to hit it a lot faster. There's a lot less contact time. So when it comes to momentum and kinetic energy, there are a lot of differences, basically in the transfer of the energy, right, which is our work. And so it is important. There is a key difference there between momentum and kinetic energy.